Hello and welcome to day 5 of the Advent of Code 2021. I will walk you through how I solved this with Kotlin once again, and along the way I'll explain what I did, why I did it, and how I finally arrived at a working solution. So let's go. I'm not going to read this, I'm just going to explain what we have to do, assuming that you either read it already or otherwise you'll figure it out right now. So the idea of this puzzle is that we receive just a list of lines, you might say, or edges, you could also say. So we have these points. So if you would consider a 2D coordinate system of sorts, that only has discrete steps, though, only integers. So you cannot have half points or any other floating points. So what we receive right here are coordinates. So 0, 9 would, well, obviously be 0 on the x-axis and 9 on the y-axis. And that is a line connecting to this other point on the coordinate system, 5x and 9y. So you see this is will make up a line from 0 all the way to 9. So you will see this will make a straight line from 0, 9 coordinate to 5, 9. Nothing super fancy at that point. So what we have to do now is essentially draw, well, we don't have to draw them necessarily, but figure out the lines that will be created when essentially applying all of these lines on a grid or something like that, such that you get something that you see down here. So you get, if you draw the lines, you will have some lines going all over your grid. And the point of this puzzle right now is to find how many points any lines intersect. So you can see right here the way they did it in the example, which is probably a clever way to do it, is that you just count for each cell how many lines go through the cell. So you see in this example here that you have a few cells that have 2, or down here as well, meaning that multiple lines went through them. So the output of your algorithm the answer to your puzzle is how many points we see it right here do overlap in this grid. Yeah, that's pretty much it. The thing that is very important right here for the part 1 of the puzzle is this other piece in bold right here, which I did initially miss. So it reads only consider horizontal and vertical lines, because of course you could have diagonal ones, right? But for the first part of the puzzle, we do not have to consider them. The important thing right here is, of course, when you solve the first part of all the Advent of Code puzzles, you do not see yet what is part 2, right? I figured though, given that they printed this in bold, I was like 99% sure that for part 2 you have to do something with the diagonal lines as well. So from the beginning I wanted to build it in a way that it will also support diagonal lines, just gambling on the fact that likely this is going to be the case. Let's see later if it was or not. Yeah, so let's jump into the implementation. So let's check out how I solve part 1. I'll go step by step. So the first thing we obviously need to do is parse this in some way that we get the actual points, right? And then we can start like drawing lines and whatnot. So the way that I did this here is pretty straightforward. So I get all the lines, my input right here. So this is my input. And I, of course, first of all, split them by new line. That's very straightforward, right? So then we have one line per line, literally. So that's first step. Second is to again split each line by this constant that I have here, connector arrow, which is just space, then this arrow and another space. So you split it by this, so you get like the 2 points on either side. And then of course in the next mapping here, I can just unpack this or destructure it, it's called in Kotlin. So this would give a list, but I know it only will have 2 elements, so I can put these parentheses around it, and then it will give me the first and the second element. If there would be more, I could also add more things here, but I know this will only have 2, and I only also care about the first 2, even if it would have more. So we have our from and our to point right here. But still, of course, firstly, it's a string, and secondly, it still has the comma, right? So we have to figure out what's the x and what's the y coordinate for each. So then the final thing I do right here is I created a point class, data class, which is literally just an x and a y coordinate. The typical thing you would do in computer science class or a course or something. And then I added a static method on that in its companion object that's called from comma separated. So all that does, it takes, well, comma separated x and y, splits it by the comma, obviously. Again, we do destructuring, so we get x and y, and then we just convert those to integers, and we can then construct our point. So this, we give it any string, and it returns us an instance of this point. So yeah, and then once we're done here with the mapping, we do this for each from and to point. And at the final step here, I pass this into a line, which I also created a data class for, which is literally just from and to reference to points. So if I pass from and to in here, then yeah, we can construct our lines, map that, and thus we return a list of lines from parse lines. Yeah, and then literally we have our lines here in the first step. The next step, as you already see right here, is I want to filter out, so filter not, right? It does the opposite of a filter. That is a diagonal line, right? Due to the reason that here it said only consider horizontal and vertical lines. So no diagonal ones. And how I did this is that the line itself has an attribute. Don't worry, there's quite some stuff going on here, but for now we only need to care about is diagonal. So once you have a line, you have a function that you can call on it, and it literally just checks. Well, how do you check that something is diagonal or not? It's pretty straightforward. You just check if either both of the x coordinates are the same or both of the y coordinates are the same, right? And if that is not the case, so neither of those is the case, so I negate this whole thing. It's, I think, Morgan's law it's called, right? And so if you negate an or, Boolean or, you get the same as if you would do and negate that. So if we have neither any of the x coordinate is the same or the y, then we know it must be diagonal, right? And thus here I can say filter out everything that is diagonal, or rather filter not it is diagonal. It almost reads like an English sentence. One of the things that is really nice about Kotlin, in my opinion. Right, so if this didn't make sense, just quickly checking here. So what this means, right? If you can be sure that something is not diagonal if you have a line, let's say that these points here are connected, then in this case you would know that their x coordinate is the same, right? They have the same x coordinate down here. Otherwise they cannot be a straight line. If neither x nor y is matching, so if you would go like diagonally, then that's the only way neither is that. So that's our is diagonal. So when I filter out everything here that's not diagonal, obviously that is perfect, because then we have our input to continue. So already, well, not quite, but already the last step sort of is to now count how many points on these lines are overlapping. Before we look at that though, there's one important thing that I have to show in the line class itself, since that is pretty important. You'll probably notice that there's quite a lot of more stuff going on right here, right? That is not simply is diagonal. So what I decided to do right here is also immediately offer that I have from and to on my line, that I can also sort of interpolate what the points are in between from and to. So if you would go here from this point to that point, we can of course figure out, hey, what are all the points in between? And I figured this is nice to have on a line class, so to say, that you can say, hey, give me just all the points on the line, right? Because it's probably something you're interested in. For this puzzle precisely, this is what we're interested in, because then we can figure out very quickly, just by having 2 points, what points are in between the two, right? Which is a line. So how I did that is the following. I first calculate the Euclidean distance between, which by the way has a typo, Euclidean, like this, I believe. Yes, that looks better. The Euclidean distance between it. So what is Euclidean distance? If you don't know this, by the way, the formula just looked up literally on Wikipedia. So I just went here on Wikipedia or any other formulary collection. So Euclidean distance simply is, if you don't know it, the distance between 2 points in like a coordinate system. You can make it one-dimensional, two-dimensional, or many-dimensional. In our case, we have 2 dimensions, right? X and Y. And the formula is pretty straightforward. You take the x coordinates and square it, plus the y coordinates, square it, and then you take a square root of all of that. So I literally just implemented that quickly right here. So we have the 2 and the from, and we do squared, so power 2, plus the y ones from and to, same, and then at the end we do square root, and that will give us Euclidean distance. Why do we need that though? To be fair, there would have been easier ways to do this. I just figured that because I had this feeling, okay, we probably are gonna need diagonal lines, what I mentioned in the beginning, I figured I'm gonna do it like this, calculating, hey, what is the Euclidean distance between the two, and then trying to find all the points in between, since that would also directly give me diagonal points, I figured. So then finding points in between two other points after knowing the distance is pretty straightforward. Although once again right here I looked this up in a formulary collection because, well, I don't know this formula by heart, but this is the formula to like when you have known when you have given I want between my 2 points, so you know the distance already, I want to go that many distance away from that, which coordinates would that give to me? So let's make it a bit more clear in an example right here. Let's say we would have this point right here, and then we want to know at distance 2 between this point and this point, what is there? So we would go from here 1, 2, so it would give us this point. That's the whole idea I had. And then you might already see where this is going, because then if we just iterate towards the other point from one point and do this step by step, we get all the points in between. That was my assumption. So what you just simply do here, or this is, well, the part that's not so simply, I guess, is this did work fine until I realized, okay, it doesn't fully support diagonal lines. The reason being that if you have a true coordinate system, right, with floating points, so not just a grid where you have like discrete integer steps, so you can only have coordinates that are like here 9, 7, right? You cannot have 9.5 and 7.1 or something, even though in a regular Cartesian coordinate system you could have that, of course. I figured that if you do like the direct Euclidean distance between 2 points, and they are also diagonal, so for instance like it is here in this diagram, that would actually not be the same distance as if you would go if you would do hops, so to say, right? Because it is always a bit less. So what I figured then is what we have to do instead is I have to separately calculate or keep track of what is the Euclidean distance to still use my formula that I already had at this point, which is, as I said, just the off-the-shelf formula to calculate where's the point given two other points. But still being able to use the fact that these are just integers, right? They're not doubles here, right? And they're just discrete steps. So what I then also did is calculate the hops. So what I mean by hop is like how much you go, yeah, like you can, because discrete steps, right? You can go 1, 2, 3, 4. Which is not the same necessarily as the Euclidean distance. If you have a straight line, it is actually the same. But if you do not have one, if it's diagonal, this will be always a bit less. So that's precisely what I do here. I say if it's diagonal, then we need a slightly different way to calculate it. What you can then simply do is take the x coordinate of one and the other, and do subtract one from the other and do an absolute on that, because then you will always have like how many hops diagonally do you go, right? You go from one x to the other. It doesn't matter if you go forward or backward due to the absolute at the end, and then you just know diagonally how much you hopped. You do not need this if it's a straight line, because then Euclidean distance is literally just the same. That's why else I just say convert this to an integer, cast it to an integer, because it will be just a floating point number, but with a 0 after the point. And yeah, the part that now is not only necessary to do is, of course, get all the points in between. So all I'm doing right here is that my line has a public field property points, which is a list of points. It is ordered in a sense that it goes from 2 from this point closer to 2. So all I did right here is say, make me a list of from, concatenate that with points in between, which we'll look at in a second, and then 2, and then I just concatenate these together. So I have like an ordered list from, all the points in between, 2. Again, I think it's quite nice in Kotlin. It reads again it's very visual, right? You say from, points in between, 2. I quite like that. And then I figured this is literally just showing off some of the cool features of Kotlin, in my opinion. I thought, okay, this is a perfect opportunity to make a lazy delegate. So super overkill, of course, for this puzzle, but the idea here just being that likely if you would use this class, and my point is a bit right, I want to bring you closer a bit, like how I would want to do this if it would be like a bit of a larger application or something, even though these are not, obviously. Then just by constructing a line that goes from and to, you might not necessarily want all the points in between, right? It needs runtime, first of all, to calculate them. It's not insanely much, but it needs time to do this part here, points in between. And secondly, it eats some memory, right? So what this lazy delegate is simply doing, you say by lazy, and then you wrap it something here in the lambda expression. Then this simply means that by default, if you do it like this is not evaluated, right? That's why you wrap it in a lambda. So by default, this variable is just empty, essentially. And then the first time you do access it, it actually runs the lambda, and only then calculates all this stuff here. So point being that if a caller of one line instance never needs the points, this is not going to be executed. Thus, some runtime is saved, some memory is saved. Quite nice. Super overkill, obviously, for the assignment. Anyways, I need all the points. I thought just this is a nice use case for the lazy delegate in Kotlin. Right, now to the part that we haven't looked at yet, which is points in between. So what is going on there? It's a one-liner, luckily. So all we have to do now, right, after we can calculate right here with this formula that I'm going to go into a bit more detail in a second, what point is from the starting point towards the 2 point, we can simply do the following. I figured I can iterate from passing in the hops that I want to go from. I'm going from 1, because of course we need the point itself is already from. So we want to start off like a distance or 1 hop away from our from point until the hops. So of course we also do not want to include the 2 point, so that's why I use until. So you can see here, this is new in latest IntelliJ version, pretty nice. You can see it's what this evaluates to. So it will be it will be that it's larger or equal to 1, this range that we would do here, but smaller than hops. So the actual numbers that we would have, let's say the hops are 3, then we would have just 1 and 2 in this expression right here, literally a range of 1 and 2. And then we just map over that, calculating the point at the distance in between for that. So let's say hops were 3, we would do just give me what point is 1 hop away from my from point and what is 2 away. And then you have 4 points, which are literally from the 2 that are in between from and 2, and 2. And that are all your points ordered in a list. So far so good. Let's look at what this does. So this is what I had to change a bit, since in the end I figured, okay, this doesn't actually out of the box work for diagonals. So the way then it does work pretty nicely is just by using the rule of 3, I believe it's called in English. So because you need to essentially calculate from the hops how much distance that is, Euclidean distance, I just do this. So you say, I have my Euclidean distance, and I know how many hops are in between the 2. So I do a rule of 3 here. So I say Euclidean distance divided by the hops times how many hops I want to go. So you essentially make this is like the relative hops per distance, and then you multiply it with how many you actually want in this iteration. So let's say 1 first time around. And then if we divide that again by the Euclidean distance, and that this large part here is simply this formula, then we have this t value right here. And then this part, yeah, there's not much to explain about it. This is just literally the formula to calculate this. You can plug it in right here, and the from and to x and y values, and then you have the new x and y values of your point that is x hops away, which is the argument right here, in between your existing from and to values, just based on the distance, right? That's pretty much the idea right here. And then the last important step is, of course, these are doubles, so we have to round to an integer because of the fact that the rounding here is not going to be perfect all the time. You will get like some rounding errors, so you have to round it to the nearest integer. And anyways, our points, of course, are integer based. So that's the last step. The thing that is actually quite nice about this is that if these would be doubled, so you would have a Cartesian coordinate system that is like infinite resolution. So you can have what I said earlier right here. You can have 9.5 and 7.4 or something as x and y points. Then, if I'm not mistaken, if we change this to double, this should directly work out of the box as well, and obviously take this away right here, because the rest of the formula is already meant for a Cartesian coordinate system. So I guess that's nice. Let's now quickly look into a bit of intermediate steps of how this looks like, and run that you will see like what the lines are looking like. So the lines, for instance, are like this. Now we have our from and our to. The Euclidean distance of that is 59 right here, and it's also 59 hops. Reason being, of course, as I mentioned, that because we filtered out all diagonal ones, the hops in the Euclidean distance are just the same, right? And here you also see now lazy value not initialized yet. So we only once we actually get the points here, then it's calculated. You see it's still pretty fast, but still it saves us a bit of runtime and a bit of memory. So what do the points look like? Nothing really interesting. It's just literally all the points on this line. In this case, it's very many, of course. And then finally we have here is diagonal. In this case, we already saw it's not diagonal. Also because here the x values are the same. Let's also quickly check this formula right here, because it is not super straightforward, I figure. So if you run that right here, and do it for 1 point here, for instance, we see this one is, for instance, a diagonal one apparently. No, it's not, sorry. It's not a diagonal one. So we now do these hops, right? So we start with 1 here. So you see that 1 hop away in between 452, sorry, and 244 to this other one. You obviously need to go just down on the y-axis. So the x-axes are already the same, right? So you just need to count up from 244 all the way to 303, which is precisely what is happening here. You see, due to rounding errors right here, because it's just a normal double, you get like some really strange looking numbers, but that's why we do round to int here. So this is nicely rounded to the actual integer. So if I would just step through now, you see that this number, sometimes it hits also nicely the proper integer. It literally just counts up now. Of course, there would in theory be easier ways of doing this. Again, as I mentioned, mainly the reason why I did this is to also support diagonal lines, because then you could also do this more or less easily by saying, okay, by going diagonally, if I go down, let's say I go like 1 to the side, to the right, and 1 down, right? That would draw you down if you do that all the time. But then the issue is also you have to figure out which direction do you go, from which point to which other one, and do you go up or down and stuff like that. So I figured this is a bit, well, I'm not sure nicer, but more generic, and in my opinion it's very like straightforward to understand what the idea is, at least. Maybe this formula is not super easy to understand, but I think the general idea of what I'm trying to do is hopefully pretty straightforward. So yeah, there's not much point in stepping through. We just step through here and you see this increases all the time. And then you see the hops here also increase. So we now say, give me something that is 23 hops away. And then we get this new thing by plugging it into the same formula all the time. So what we have then, and as you can see, this is not calculated yet, right? But it's like initialized, so to say. once we have our line, we also have the points, even though they're not yet like actually computed, but the property is already there to be accessed. So all the magic, let's say, happens in these 3 functions right here. This is literally all that is doing the heavy lifting. So to summarize quickly again, we get from all the distance in between one and the other point, we calculate each point that is so many hops away from there. And because hops meaning that since we have a grid that is discrete integers, we can just hop forward essentially. So we would indeed do like 1 distance, 2 distance, 3 distance, and that's it. And we also have our start and end point. And then literally if we just concatenate all these things together, we have all the points on that line, which is this property. So once we have that, the rest is very straightforward. So all we now have to do, I figured, is there's not really a point in drawing this grid actually, right? So they make it here because it's nice and visual, right? And at first I thought, okay, I'm just gonna draw the grid now because I have all my points, all my lines, sorry. So I can now just iterate over all the lines and draw them on the grid. But it's not really necessary, because the only thing we're actually interested in is which points do we have? Not even caring about what the actual lines are, right? We only care about the points, really. Which points appear twice, so to say, which are duplicates if you want. So what I'm trying to do now as the final step is in here, once we have our lines in the collection and we filtered out all the ones that are diagonal, we, even though it's not necessary yet, it is supported down here with that this would support diagonal lines, although we actually do not need them, but yeah. Now we can just count how many overlapping, and this is super straightforward now, because all we need to do is we flat map of all the lines, we just get all the points. So we have a flattened list of all the points on any line. We don't even care anymore on which line they are right now, right? We could even shuffle this right now. The order doesn't matter. This could also be a collection. It doesn't have to be a list, really. Yeah, as a matter of fact, let's make it a collection just to like really show that that the order doesn't matter. And then simply what I do is I group all these points by themselves. So what is group by doing? It gives you a map of whatever you group by as the key, and then all the values that have the same property in whatever you match here by as a list in the values. So we could also say here, give me everything that has the same x coordinates. I don't know. So yeah. But then by default, what this would give us, let's say we plug it into a variable, this would be a map of point to list of points, right? So we would just know at this point on the coordinate system, which points are there, or these 2 x and y values, if you want, which others are there. That's actually not super helpful. What we do want to know is how long is this list, what's the size of this list, right? Because that would tell us how many points are at this exact other point, which they did on here by counting this number here. So you see, like, there's 1 point at this coordinate, but there's 2 at this one. So then if I just say map the values, and by just counting how long this list is, so the value, you remember, was list, so we just count length of the list, which now gives us a very nice map a map from point to int. So we now just simply know at this point on the coordinate system, there's this many instances of some line that has a point there. So literally last step now is we do not care anymore about the key of the map, the keys. We only care about these. So we literally just count now how many of the values are larger than 1, right? That's what would it be an intersection. If there's a 1, that's the only one that is there. So only thing we're interested in is 2, 3, 4, anything higher than 1, and that will give us an int. And that is literally how many intersecting points there are. And then if we look here at how many points do at least 2 lines overlap, if we run this right here, we would get precisely that. And now let's go in here and quickly check this map, so that is a bit easier to understand. So if we now just flat map all of our points, you see we have more than 100,000 points. But now we can just group them. So we now see that at some points, like this one for instance, there's only a single one that is overlapping. While at others we see there are some some more that do overlap. So for instance, now if we would say point frequencies filter its dot value is larger than 1, we would get from 100,000 to 5,000, which are the ones that are more. And you see at some cases there's 2 points that overlap. Some other times we might also have 3, maybe not, or even 4, even 5. Maybe it's only the diagonal ones. Here's only always 2 apparently. Yeah, it depends on the input, obviously. But this is this map you have from these 2 coordinates. That's how many clash there, so to say. Yeah, and with this knowledge, this is, you can see already this number is the same as the output at the end. There we go, 5,747. Let's quickly jump to part 2. You will see why in a very few seconds. So you maybe remember at the beginning when I said, oh, my suspicion is that, or was when I solved it initially, and you don't see yet the text of part 2, right? Probably gonna need diagonal lines at some point. Turns out, was it precisely true? This is literally the same puzzle, with the only difference that you have the same input, but you now also consider diagonal lines. And you again do the exact same. You draw, or how I did it, by like counting how many are on the same coordinate. How many points do at least have 2 lines that overlap? So you do exactly the same, which means in my case this was very nice in the end. If we have solved part 2, it's exactly the same code, 1 by 1, with the only difference that we do not filter out the lines that are diagonal. So this is literally the part that I marked here is what is not there in part 2. Everything else is exactly the same code, because now we do consider diagonal lines, and that gives us way more things that are overlapping, obviously. Right, and that was it for day 5. If you do have any questions, please drop me a comment below. I'm very happy to answer them. And yeah, if you also participate, make sure to join my leaderboard, which the code for that you'll find in the description under this video. And apart from that, like and subscribe this video if you enjoyed it, and I see you tomorrow. Tschüss.